Hello everyone. Welcome to this Royal Society of Tasmania webinar. I'm Jocelyn McPhee. I'm the Vice President of the Royal Society and today standing in for President Mary Koolhof, who is not well. Today, we are meeting on the country of the First Nations of Lutruwita, Tasmania. The Royal Society of Tasmania acknowledges with deep respect the traditional owners of this land and the ongoing custodianship of the Aboriginal people of Tasmania. The Society pays respects to elders, past, present, and emerging. We acknowledge that Tasmanian Aboriginal people have suffered severe and unjust impacts resulting from invasion and dispossession of their country. As an institution dedicated to the advancement of knowledge, the Royal Society of Tasmania recognises Aboriginal cultural knowledge and practices and seeks to respect and honour these traditions and the deep understanding they represent. Thank you everyone for joining this afternoon. Just a few points about the webinar. It is being recorded. The chat function is disabled, so you won't be able to use that, but the Q&A function is operating. So if you have questions that you want to ask our speaker at the end of the webinar, then you can type them into that Q&A and I'll read out as many as we can. So our speaker today is Dr. Adam Abersteiner. Adam is a postdoctoral fellow at the University of Helsinki in Finland. And that's why we're actually meeting a bit later than normal. So Adam didn't have to get up too early on his Sunday morning. And it's also why this is only a webinar. It's one of the wonderful things about webinars that we can in fact have this, this lecture at all. Adam is one of two winners of the Royal Society Doctoral Awards from last year. These awards are intended to recognise outstanding PhD research. In Adam's case, his PhD thesis was on a very special kind of igneous rock called Kimberlite that comes from a magma formed very deep in the earth. And it's a very challenging rock to study because of its special origins and characteristics. He was focusing on using a very sophisticated technique to track the origins of kimberlite magmas. And he's going to tell us a lot more about that topic now. The title of his talk today is Kimberlites, Volcanic Insights into Earth's Deep Interior. So over to you, Adam.
Yes, thank you, Jocelyn. First of all, it's a great honor to be the recipient of such an award and to have some of my work recognized at large. So the topic of my talk today will be on kimberlites. So why kimberlites? Kimberlites, they're an interesting type of rock as they represent some of the rarest yet most fascinating rock types. These rocks originate from the Earth interior, but their origin still remains very elusive. So before I get into this, I would just like to make a few acknowledgements. First of all, to my PhD team, to first of all, Dima Kamenetsky, who is my primary supervisor throughout my PhD. And it's without his knowledge and guidance, and none of this would have been possible. But of course, to Maya, as well, and of course to the CSL team, people Sandrin, Thomas, and Carsten, who made a lot of their analytical work possible. And of course, throughout my PhD, there was numerous help from a wide range of people from, around Australia and from abroad, namely from Canada and from across Russia. So a little bit of background before I get into talking about all the detailed information is like, why the PhD life? I mean, it's not typically the path taken by most students. Most people, when they do a university education, they're desperate just to get a undergraduate degree or an honors or a master's, get out of there as quickly as possible, find a job and get paid. So why necessarily motivate myself to endure an additional 3 to 4 years of grueling, intense study, research, and scraping by on minimal wage? So I started my undergraduate back in 2011, and geology was, a very serendipitous discovery. I merely chose it as a subject to fill my timetable. It was never a subject taught in high school, so my background on it was very minimal. But I was quick to adore this subject, as you get to go outside and explore out in nature. And back at the time, there was the mining boom going on. I mean, people were going headhunting students to go work in the mining industry. It's like, okay, you can identify a white mineral, you can identify a black mineral. Great, here's a $100,000 a year job, go move to Western Australia. But unfortunately, by the time it reached around 2014, 2015, as I was completing my undergraduate and honors degree, those days had come to an end, and no longer was undergraduates desirable in the mining industry. I mean, someone 10 years in the industry was getting laid off. What hope did this fresh out of university student have? So with limited choices and a supervisor nagging at me to continue my research, I decided the next reasonable course of action would be to do a PhD. And so I guess most people think of the typical depiction of a PhD in geology to be extremely stressful, this panicked race towards finishing a thesis. However, I would say that my experience was much more positive than this. Please note that the yellow line, that this will to live line, never actually achieves zero, so it never reaches that stage of desperation. And as for anyone curious as to rock licking, it is a legitimate field technique for identifying salt minerals, clays, and doing grain size analysis, but I wouldn't recommend licking rocks as a non-geologist. But anyway, to more serious matters, why exactly kimberlites? Well, as I mentioned before, kimberlites are the deepest probes into the Earth's interior. So where the importance of this sits in is that we exist on the very thin outer layer of the Earth's crust, and beneath us is a very complex interior which we have very limited knowledge and access to. I mean, you consider that core is around 2,900 kilometers deep, and the overall radius of the Earth is 3,500 kilometers. And we, living at the surface, can only study what's available to us at the surface. And yes, even the deepest attempts to drill was a scientific endeavor during the time of the Soviet Union, which only achieved a depth of 12 kilometers. And this is, when you put this into perspective, this is less than 0.5% of the way to the Earth's interior. So how else are we able to understand what's going on in the Earth's? Okay, there's several direct and indirect ways of studying the Earth interior. One is using meteorites, as they're some of the primordial building blocks of the solar system and Earth. And they tell us a bit about the bulk components of the Earth. However, since then, the Earth has differentiated into forming different components, such as the core, mantle, and crust. Another way is using geophysics, as seismic waves can be used to determine the structure and mechanics of the Earth interior, as seismic waves behave differently when passing through different materials. Another way is using volcanic processes, as volcanoes often bring deep material from from the Earth to the surface, and occasionally they pick up inadvertent pieces of rock, or termed xenoliths, which act as which are carried up by magmas as passengers to the surface. Or alternatively, during plate tectonics, sometimes when plates are converging, material is sometimes thrust to the surface, or material which is otherwise buried normally at depth is brought up for us to study. And these give us access to deep rocks that are otherwise inaccessible at the surface. And this is where the topic of kimberlites comes in. A little bit of background on kimberlites. These were the association was discovered or began back in 1866 when there were diamonds discovered in the Cape Colony of South Africa. This discovery of alluvial diamonds soon sparked a major influx of prospectors into Southern Africa, but soon, not long after, these non-alluvial deposits were discovered, leading to two deposits being mined by the De Beers brothers. One was the De Beers mine and the other Kimberly. It soon became apparent that these diamonds were hosted by igneous rocks, and these were described as explosive tuffs and subsequently named kimberlite in honor of the adjacent town. And soon after, the entrepreneur Cecil Rhodes established the De Beers Consolidated Mines Limited, which would soon go on to be a mining magnate throughout much of the 20th century, until diamonds were soon, or kimberlites were soon discovered in other regions of the world, namely places like Russia and Canada. This represents the deepest excavated hole done by hand. So, excuse me. So kimberlites. When you think of a volcano, most people think of your typical nice cone shape, majestic lava flows and all that. You can see like Mount Stromboli or Mount Fuji here, for example, but kimberlites represent something very different. They don't form these big cone structures. Instead, they are thought to ascend so fast from deep depths within their mantle. So it's estimated at least 150 kilometers deep down within the mantle, and they're thought to ascend at rates within a matter of hours and days to the surface. So these are incredible distances traversed by the magma, and by the time it reaches the surface, it creates an extremely explosive eruption, which essentially excavates a hole in the ground, forming these carrot-shaped pipes or diatrams. And unfortunately, no kimberlite eruptions have ever been witnessed within the human existence, as the last major occurrences occurred around 30 million years ago. However, there is a rare case of some extrusive lavas occurring in Tanzania, which are about 10,000 years old and are thought to represent some of the most, or the youngest, manifestation of kimberlite magmatism. So where exactly do you find kimberlites? It's notable that kimberlites occur across all continents on Earth, including Antarctica, but however, it should be noted that no kimberlites are ever found in the oceans. And of all kimberlites discovered, only around 10% of them may contain diamonds, and perhaps less than 1% of them may be considered an economic grade. And these association of diamonds and continents becomes, more interesting, as kimberlites are only found within cratons. And cratons, represented by these blue regions, these represent the oldest surviving areas of continental crust, which were the nuclei for continental landmasses and have remained virtually unchanged since their formation eons ago. Thus, kimberlites eruptions are only typically restricted to areas of certain types of crustal structures. Now, once a kimberlite is located, they're typically mined as open pits or later underground. And you can see these enormous excavations occurring. And the surface expression of the kimberlite is often very hard to detect. And as they often form these very flat forming craters, and over time, they're heavily eroded, and essentially they form no surface expression. So it's typically through geophysical techniques or indicator minerals that their epicenter is able to be located. And in rare cases, often they're located under lakes, such as in Canada, where they occur in like very, I guess, the lake districts in the far north. So why exactly are kimberlites important? One of the first reasons, and perhaps the most obvious, is diamonds. Diamonds are highly sought after for jewelry and for industrial purposes. It's estimated maybe about 20% of diamonds are considered gem quality, and a further significant proportion contain inclusions. And large diamonds, such as this one discovered just last month, which is considered the third largest gem quality diamond ever discovered, these are extremely rare. So, the second reason why kimberlites are very important is they represent the deepest derived magmas. It's estimated they form at depths of 150 kilometers or more, but where they form or the original depths that they're generated at is still widely debated. It's typically thought that they form at the base of the lithosphere in these regions. However, they may also be thought to be associated with subduction-related events, as pieces of crust at the surface are dragged back down into the mantle, or be associated with even deeper upwellings of magmas from the deep earth interior. Now, the third reason why kimberlites are extremely important is mantle xenoliths. Xenoliths, these represent inadvertent pieces of rock which are plucked from the surrounding, I guess, inside the conduits and carried by the magmas to the surface. Because kimberlites come from great depths, they pick up some of the deeper to the surface. There's been minimal time for these rocks to react or re-equilibrate. And this allows for some direct study of the mantle. So these are some of the three reasons why kimberlites are important for direct study of what goes on in the Earth interior. So coming on to my task, which is understanding the origin of kimberlite magmas. Despite all this background information we have on kimberlites, they still remain an elusive type of magmatism. Our understanding of where and how these magmas are generated, along with the triggers that cause them to ascend so fast to the surface, is still incomplete. By the time we look at a kimberlite rock, it's no longer representative of the magma that was generated in the mantle. So during a kimberlite magma ascent, coming from the deep surface, it often carries abundant crustal and mantle xenoliths. And these are often just entrained in the magma, or sometimes they can be assimilated or essentially melted and incorporated into the magma, therefore changing its composition. The second reason is that there's significant degassing of volatiles, so components such as carbon dioxide and water, which are thought to be major components in the magma, are often lost due to changes in temperatures and pressures of the magma as it rises. The third reason is that kimberlites often explosively erupt, or magmas may differentiate, where different components may, for example, be gravitationally separated. And this often mixes up the material a lot. And a fourth reason is that after the magma is in place and solidifies, we often have fluids infiltrating from the surrounding rocks, where you have meteoritic fluids coming from above or hydrothermal fluids circulating in the local geology. And this causes a dissolution or reprecipitation of minerals. So, and finally, because of their old age of kimberlites, many of them are heavily eroded. So we often don't have access to their original samples which were erupted at the surface, because hundreds of meters of erosion of the kimberlite edifice may have been removed since its emplacement. So essentially, we don't fully understand what the original kimberlite melt at depth was like prior to all these modification processes. So essentially, when you're looking at a kimberlite rock, it's just like a trash bag of mixed material. So then, how do we gain insights into the origins of kimberlite magmas? How do we know what's going on deep here, as opposed to all the processes of contamination as it rises to the surface? Now, one particular way is to look at inclusions in minerals. Now, inclusions are common in minerals, and these represent small pockets of melt, gas, or other crystals that become entrapped during the growth of a host mineral. And for example, in the world of gemstones, these things are generally avoided, but also they can be used to distinguish whether a material is natural or synthetic. So essentially, melt inclusions represent the parental or host medium from which a crystal grew from. When a crystal is growing in a melt, the surface is not always even, and sometimes embayments form, such as here, where inadvertently pockets of melt, fluid, or other crystals are entrapped. And quite often, inclusions occur in different generations, and this tells us different information about their parental medium. And this will be explained a little later. So, inclusions, where and how they form. So, once entrapped, inclusions are generally protected, and they prevent additional modification, or in essence, they represent a small parcel of melt frozen in time. Furthermore, it may prevent the loss of any components or volatiles once they are sealed, as changes in pressure and temperature may cause different reactions to occur. And furthermore, they're protected from post-crystallization, modification by fluids, or otherwise alteration of the rock. So in order to gain further insights into kimberlites, I tried to take a representative sample of kimberlite material from different locations from some of the larger kimberlite provinces around the world. And the goal was to acquire some of the most fresh and most pristine material, or otherwise the material which has been least affected by this hydrothermal or meteoritic erosion or modification. So unfortunately, no direct field work was possible, as many of these samples were passed on by various collaborators. Quite often, kimberlites are often in the possession of diamond mining companies, which often means that they commercialize, and it's not so easy just to walk onto a lease and start plucking rocks. How kimberlites may look, for example. This, for example, shows some field expressions of kimberlite outcrop, and just looking at a weathered surface like that, you wouldn't guess it's a kimberlite. And quite often, it's very hard to find fresh surface expressions of the rock. And you can see here, this is taken from a game reserve in South Africa, as represented by the mass graveyard of skulls of some type of creature. Or alternatively, through deep drilling of material. Quite often, you can acquire material from hundreds of meters down, or alternatively from, active mine sites. And these are just some of the examples of field relations of kimberlite rocks. For example, if you look at the volcanic clastic kimberlites, they represent a chaotic mixture of materials, a wide assortment of mixed material. And essentially, volcanic clastic kimberlites, they've essentially been magmas which have been exploded, highly fragmented, and then essentially stuck back and welded back together. So essentially, after we've collected rock material, the first step would be to polish down the material into what we call thin sections. And essentially, thin sections represent 30 micron thicknesses, or essentially, several times thinner than a human hair piece of rock. And thin sections essentially represent the bread and butter for our ability to understand rock textures, mineralogy, and eventually determine many aspects of the petrogenesis of rocks. And by polishing it down to this thickness, it allows us to pass light through crystals and understand their optical properties and identify minerals. And optical microscopy, this is the backbone of petrographic research. It allows us to essentially augment our ability to identify minerals and in the case where minerals are transparent, for the identification of melt inclusions. Now we can step this up a notch and take this to various microbeam techniques, such as scanning electron microscopy or the electron microprobe. And essentially, by firing a focused beam of electrons onto a surface, various signals are produced. This allows us to produce images or understand the compositions of materials at much greater resolutions than with a regular optical light microscope. And for example, the panel on the left shows a thin section under high magnification, and we'll see that it produces these black and white images, where lighter images are represented and these dark images are represented by differences in the relative composition of the material. And the other shows the high resolution data that's able to be obtained by microprobe analyses. So just to quickly summarize how these techniques may be used to identify melt inclusions, we take some material from the field, polish it down into a thin section where we're able to pass light through the material and observe the mineralogy. And in the cases where melt inclusions are present within materials, we're able to identify them and isolate them, and then analyze them at very high magnifications using the SEM. And then we can use the various signals produced by firing electrons at them to analyze the individual elemental compositions of these phases included in these inclusions. And for example, in this case, we have a very high potassium and chlorine signal, so we can determine that this mineral is a sylvite, or essentially the potassium variant of regular table salt. And this shows some examples of some melt inclusions under a scanning electron microscope. And we can see that they're extremely complex in composition, and their daughter mineral assemblages. They contain both plethora of kimberlitic and exotic phases. And quite commonly, they're very unstable, but it's not relevant at this stage to know what all these compositions mean, as later on their significance will be unveiled. So to further investigate the complexity of these inclusions, we can use X-ray element maps to allow some 2D perspective how elemental abundances are distributed across complex or mineralogically complex melt inclusions. This allows us to further enhance our ability to understand the mineralogical diversity of the inclusions. And by determining the chemical compositions of the inclusions, this is essential for using melt inclusions to interpret different magmatic processes that may occur. Other ways of analyzing inclusions is through heating experiments, by essentially putting individual grains, which may contain inclusions, in a heating stage, and underneath an optical microscope, we're able to artificially increase the temperature, and we can provide details on the homogenization temperatures, which provide details on how inclusions behave during melting and cooling, as well as the minimum estimates of which inclusions interact. So by heating it from ambient room temperatures, we can see phase transformations until eventually it reaches a homogenized liquid inside these inclusions. And for example, in this case, we can see this inclusion homogenizes at 667 degrees, and we can extrapolate that this was the minimum temperature at which the inclusion was entrapped in the host mineral. As it cools down, you can see that the inclusion recrystallizes into individual components. Another technique for analyzing inclusions is using Raman spectroscopy. In some cases, when we're looking at a inclusion and exposing it at the surface, sometimes these inclusions may contain a fluid phase or a gas phase, and by polishing the surface, you're going to lose this fluid or gas phase. So sometimes there are inclusions which are buried beneath the surface of the inclusion. And Raman spectroscopy is a technique that allows us to determine the chemical structure phase or crystallinity of a molecule. So essentially this works by firing a laser at a material, and their interaction of light upon a molecule creates a scattering of light. And depending on the type of molecular bond caused by the vibration, by this interaction of light, the scattered light may be used to interpret numerous aspects regarding the chemical structure. For example, if we have an inclusion and we fire a laser at it, we get a clear signal response. And in this case, this response would tell us that this particular phase corresponds to the mineral calcite. And this shows another example of firing a Raman laser at an inclusion. And the host mineral is olivine, which is represented by this distinctive signal. But also we pick up another distinctive signal, which corresponds at these particular numbers, and that corresponds to carbon dioxide. So we can say that there's a strong carbon dioxide component within this inclusion. An additional technique, which is quite a mouthful to say, is laser ablation inductively coupled plasma spectrometry, or in short, LAICPMS. Now, this allows for very high sensitivity elemental and isotopic analyses of materials. So it's divided into a laser component and the analyzer, or the ICP-MS. Now, this essentially works by firing a beam onto a material, and essentially it ablates the material, turning it into very fine particles. Now, these particles are carried by a gas into the ICP-MS, where it becomes ionized by a plasma, and this plasma is transported into a mass spectrometer and analyzed, where trace elements down to levels of parts per million or even parts per billion can be determined. And this is very useful for determining trace element distributions in any given material, or in our case, inclusions. For example, this shows a typical spectra of what a ablation signal looks like. So the y-axis just representing, counts, whereas the x-axis represents time. And as time progresses, the laser is drilling deeper and deeper into a material, and we can ascertain where the individual inclusions occur and gain an idea or a qualitative understanding of the trace element compositions within an inclusion. Now, as I mentioned before, that inclusions occur in different generations, and this can provide us different information depending on the timing of which an inclusion is entrapped. Now, there are three types of these inclusions. The first of all is primary inclusions, a second is secondary, and the third is pseudosecondary. And I'll just gloss over this systematically. So, for example, primary inclusions, these are entrapped at the same time as when a crystal is growing. So for example, in the case we have a olivine crystal, and if we have an additional growth of a zone around in this olivine crystal core, sometimes that during the growth of this additional darker zone, we might have inclusions entrapped along this interface. And this is just a real-world example of olivine crystal, where we've had a pre-existing core and an additional zone develop or crystallizing on top of it, and entrapping abundant inclusions within this exterior zone. And this is just another example showing where we've had an additional growth stage of olivine, and it's managed to entrap many individual inclusions within it. And upon further magnification, we can then use this information to identify individual phases and understand the composition of these melt inclusions. Other examples show us that essentially primary inclusions, they may occur as clusters of randomly distributed inclusions or aligned along crystallographic orientations, or again, maybe orientated along growth zonation. So the second type of inclusions that may occur are secondary inclusions. Now these essentially formed by any process after crystallization of the host mineral is complete. For example, if we have the crystallization of an olivine grain, and then later on this olivine grain becomes fractured, melt is then able to enter along these fracture planes, and then through a process of fracture healing, individual little pockets of melt will be entrapped within these fractures. For example, these are some photographs, and we can see that these inclusions occur as clusters, but when put into 3D perspective, they'll always be orientated along a specific healed fracture plane. And then the third type of inclusion, pseudosecondary. Now these are somewhat more ambiguous as they're broadly intermediate between primary and secondary in origin. They look secondary, but essentially they're formed during the growth of the host crystal if it fractures during formation. For example, if we take that same olivine grain, and if it happens to fracture and melt infiltrates and becomes healed, it looks secondary in appearance. But later on, we may have a case where an additional growth zone of olivine occurs. And essentially, we see that these fracture planes terminate within individual, growth zonation boundaries. Now, this shows some example where we have pseudo-secondary inclusions, and we see that these inclusion trails terminate at the boundary of new growth zones. This is just another example, and we see a olivine core, and we see that it's traversed by these trails of pseudo-secondary inclusions, which all terminate at the boundaries of new zonation. So something important noticed during this study is that many of the phases contained within these inclusions are very water soluble. So a typical technique during the preparation of samples is using water as a lubricant. But if you're using water as a lubricant and you have daughter minerals composed of minerals such as salts or alkali carbonates, which are highly susceptible to water interaction, you're going to lose them during sample preparation. And these show a couple of examples, which are inclusions composed of salts or alkali carbonates, where upon several days of atmospheric interaction, the atmospheric moisture has interacted with them and caused essentially them to spew out onto the surface of the sample and recrystallize, forming these very irregular shapes. So a specialized technique was to use kerosene as a lubricant. So there were many dizzying hours in the laboratory using kerosene as a lubricant and inhaling these fumes and having this stench on your hand for hours on end. But in essence, it was all for the science. So yes, sample preparation is key, especially in the case of analyzing these inclusions in kimberlites. So just to quickly recap, the inclusions are very complex, both mineralogically and compositionally. But as we begin to see across all the samples we analyzed, that all the minerals contained within these inclusions, regardless of the kimberlite locality, whether we're looking at ones in Russia, Southern Africa, in Canada, in Finland, we observe an emerging trend in what these inclusions are composed of. We begin to see that inclusions are commonly composed of these alkali earth-bearing carbonates, these chloride minerals and phosphates, whereas less common are silicate minerals, oxides, and sulfates or sulfides. So how this is reflected compositionally, we see that they're essentially low in alumina and silica, highly enriched in carbon, or which comes in the form as carbon dioxide or carbonate minerals, very high in alkalis or alkali earth elements, as well as halogens such as fluorine, chlorine, phosphorus, and sulfur. So starting to put this all together, what does it all mean? What is the significance of all of this? What we see is that the kimberlite melt is sampled by these inclusions, and it may range from the kimberlite melt generation deeper within the mantle through to its ascent in the mantle and crust, or upon its emplacement and crystallization in the crust. And essentially what these melt inclusions are good for is that they're shielded from alteration processes such as weathering and secondary fluid infiltration, which is a significant process which overprints the composition of kimberlite rocks. So essentially, melt inclusions exclude this process from modifying their composition. So what does this all mean? What are these melt inclusions telling us? So the information regarding melt inclusion compositions becomes important as the melt-dating trap starts to contradict classic views. These classic views suggest that kimberlites may originate from essentially silica-poor ultramafic or high magnesium melts with variable amounts of carbon dioxide and water, whereas potassium is very low and sodium and chlorine are very low or essentially absent. However, using these bulk rock compositions, we're using a fully crystallized kimberlite rock, which is the end product of extensive magma contamination. So bulk rock analyses do not necessarily represent what the kimberlite melt is, as essentially bulk rock is just taking a rock, crushing it up, throwing it in an oven, and analyzing for its major compositions. However, this process is unable to take into account the amount of foreign mantle or crustal material that was incorporated into the kimberlite magma, or potentially the amount of volatiles such as carbon dioxide or water that's lost during magmatic processes, or furthermore, the amount of alteration that has contributed to modifying the major element and trace element ratios, or potentially removal of water-soluble minerals. On the other hand, melt inclusions are suggesting that this kimberlite melt originally contained appreciably more carbonate and was, essentially more enriched in alkalis, alkali earths, and halogens. So where did all these components go? So if the kimberlite rock is telling us one story and the melt inclusions are telling us a different story, what happened to all these components that we see in melt inclusions? One process that may commonly remove these components is from degassing of volatiles. And as pressures and temperatures change during the ascent of a magma, volatiles, their solubility and stability of volatiles within a magma change. And sometimes this is heavily enhanced by crystal melt reactions that occur within the rising magma. And then the second may be through alteration as hydrothermal or meteoritic fluids begin to infiltrate within the crystallized kimberlite rock. Minerals may be dissolved and removed or reprecipitated. And for example, as we've seen in the example of sample preparation of carbonates and chlorides, these minerals are especially vulnerable to water interaction. So what is the implications of all of this? Well, essentially kimberlites may originate from melts which were appreciably more carbonate-rich in composition and less silica-enriched than what these bulk rock analyses are telling us. Furthermore, kimberlites may contain less water than previously thought, as a lot of that may have been introduced by secondary processes, such as water infiltrating from meteoritic or hydrothermal sources. Additional components such as alkalis and halogens may have existed in greater concentrations but removed by alteration. as many of these components are often hosted in highly unstable minerals, which are very susceptible to alteration. And essentially, by alluding towards a more carbonate-rich melt, this composition melt could explain many additional properties of kimberlite magmatism, such as its high buoyancy, its high ascent rate, and low crystallization temperatures. And so to put it in a little bit of a perspective, if we were to take the average composition of a kimberlite rock and apply what is reconstructed from melt inclusion information, we could possibly deduce that the original kimberlite melt contained possibly less silica and magnesium, as silica and magnesium would have been introduced into the kimberlite melt through the interaction of mantle material, mostly through the assimilation and incorporation of mantle minerals into the melt composition, and appreciably less water, as this may have been introduced from a secondary source. And based on analyses of these daughter mineral phases in melt inclusions, we could possibly deduce that components such as the alkalis, which is potassium and sodium, as well as halogens, along with carbon dioxide, which would most likely be manifest in the form of carbonate, were much higher. Now, to take this into perhaps a real-world example, which may be comparable to how kimberlites may have looked when generated in the mantle, are carbonatites. Now, carbonatites and magmas essentially compose dominantly of carbonate, and the example shown on screen is the Oldenburg-Lengai carbonatite in Tanzania, which represents the world's only active carbonatite. Now, this carbonatite extrudes lavas, which are very alkali-rich, and which are almost analogous to the composition of the melt inclusions we observe in these kimberlitic minerals. And as we see that upon solidification of these lavas, they undergo almost instantaneous degradation. For example, here we can see these white crusts developing, and this occurs within just a matter of hours to days after their crystallization at the surface. So to not get confused and say that they're exactly the same thing, kimberlites may be somewhat analogous to what these lavas are like in composition, only generated deep within a mantle, and they may only acquire essentially their kimberlitic flavor only upon extensive interaction and entrainment of various crustal and mantle material during their magmatic ascent. So, although we've been able to gain many insights into what kimberlite compositions may have been like based on melt inclusions have only provided us a basis to understand what kimberlite melts what they may have been like, but there's still not a definitive answer. And although great progress on understanding kimberlite melts has been achieved, their original composition in the mantle still remains not fully understood, as there are still a lot of variables that can change them. And furthermore, there's still many unknowns. Where do we get these components from in the mantle? Were they, for example, perhaps derived from subduction or other deep mantle processes? And what are the tectonic drivers that generate such magmatism? So that brings to the end of the technical bit of the presentation. And in case anyone may be wondering, could there be any association of kimberlites or diamonds in Tasmania? Well, there actually have been reported occurrences of diamonds in Tasmania occurring as alluvial diamonds within the Savage River region, so up in the northwest region here. Some of them have been verified as diamonds, but there's very limited information and speculation is widely varied. As for kimberlites, it's very unlikely, as Tasmania doesn't sit within the type of tectonic or geodynamic setting which would be conducive to the formation of a kimberlite magma. But there has been one such report, one by Ralph back in the late 90s, which has provided some speculation, but there's been no serious endeavor to try and understand what the origin of such rare and sporadic diamonds is. So in case if anyone is interested in further reading of more technical works, there's a list of publications. Yeah, I guess it's best just to search my name into some engines such as Google Scholar or Scopus, and yep, that is the end of my presentation. And just to give a bit of a heads up, I am now living and working in Helsinki, working as a postdoctoral researcher since about August last year. A bit of an awkward time to be moving within the midst of a global pandemic, but the Finns seem to manage to do wonders in terms of maintaining this COVID pandemic. So a bit of my tasks is operating their LA ICP-MS facilities here and expanding onto new projects, not just kimberlites anymore, such as chromites, alkaline magmas, and different forms of intraplate magmatism. So in conclusion, thank you very much for tuning in to this presentation on your Sunday evening, my Sunday morning. And yeah, it's been a pleasure to talk about my research. And if you have any questions, I guess there's some time now, or I guess my email is listed here. So I guess I can pass this back on to Jocelyn.
Thanks very much, Adam. You've certainly advanced our knowledge of kimberlites. And also thank you for clearing up that question about whether we're going to find diamonds in Tasmania. That's bound to have been a question plenty of people wanted to ask. We do have time for questions, and if you have one that you haven't already typed into the Q&A, please go ahead and do so. While you're doing that, I'll begin with some questions that are already up and running. One is that, is it surprising that in fact these very deeply sourced magmas have such a high content of volatile elements and compounds like carbon and sulfur and the halogens? Is that taken as something very special about the area that they come from in the mantle?
I guess the association between the two, well, these particular components such as volatiles and halogens are important components for lowering temperatures of melting. And that's perhaps why we have such specific melting domains deep in the mantle. But as where these, I guess, components and how they're concentrated in particular in these zones in the mantle exactly is still speculative. Like, for example, whether they're introduced from deep mantle subduction, where we may have volatiles, components or halogens existing at the surface, and then subducted and recycled into the deep mantle, is still a matter of speculation. I'm not sure exactly if that answered the question.
No, that's fine. That's fine. Another one about a specific image that you showed of an olivine crystal that had a core relatively free of inclusions and then a rim with lots of inclusions. Why does that happen? Why is that early stage of growth, there's been no trapping of inclusions and then a whole lot of them are trapped?
Oh, it's actually speculated that the cores of olivine, actually they're xenocristic. So they actually believe that during the generation of the magma, sorry, I'm just going to close my window. It started raining and it's very loud. So the cores are actually xenocristic. So essentially you've had this disaggregation of mantle peridotite material, and the cores were essentially pre-existing mantle material, and that the rims forming around the olivine cores, they're truly magmatic, crystallized from the kimberlite melt zones.
Okay. And now one more about how your research might be used, if you can see it being used in diamond exploration? Is that a sort of an area that your research might be applied?
Well, there hasn't been any attempt to make any intricate links between diamond or this kimberlite prospectivity and what we observe in kimberlites. The specific choice of kimberlites used in this research was aimed specifically at freshest material, not necessarily the most diamond productive. I mean, taking material from both diamond bearing and diamond free kimberlites and observed similar trends. That has been no intricate links, and so I haven't sold my soul to the industry quite yet.
Right. And probably one final question. Having very high volatile content, as you've explained, for the kimberlite magma, that would normally mean a kind of magma that can flow very easily. So what would be called a very low viscosity magma. And so the question actually relates to the explosive eruption style that you said was important in kimberlite eruptions, because normally low viscosity and explosive eruptions don't go together that often. So I'm just interested to know how you see those two being aligned in the case of kimberlite eruptions.
Yeah, I guess in the term of low viscosity, this would allow for a very fast, penetration through the overburden or overlying rocks during its magmatic ascent. But because of this very high, volatile content, very carbonate-rich magma, as it rises, it becomes progressively more out of equilibrium with the surrounding wall rocks. And through melt rock interactions, you have this liberation of a lot of carbon dioxide. For example, it's speculated, because we never observe a mineral such as orthopyroxene, which is a very common mantle mineral in kimberlite, or in the mantle, sorry. And it's speculated that this carbonate melt reacting with orthopyroxene en masse causes essentially a huge liberation of carbon dioxide, which propels kimberlites to ascend even faster and more dynamically towards the surface.
Well, that makes sense. Thanks very much, Adam. And one just appeared on the Q&A. Yeah, so it now remains for me to thank you for all the time and effort that you've put into your seminar today. Very much appreciated. But also to offer our collective congratulations. It's not easy to win one of the Royal Society Doctoral Awards. We only give 2 each year, and they really do demand outstanding performance. So normally I would be offering you the certificate and the check that goes with the award. That can't take place in person, but we will make sure you get the certificate. And I think, in fact, you've already received the payment. So we're almost square. So thanks very much, Adam. And if you could put on, we've got the closing slide up there. Do you have any last comments?
Well, I guess it's a big thank you to the Royal Society, and it's been an absolute pleasure to give the talk today, and it feels like, a good sense of achievement that the hard work and hours put on throughout the PhD has been recognised. Yeah, it's been enjoyable to present today and put my talk into a bit more layman's terms rather than this very esoteric perspective that I'm engulfed in most of the time.
Sure. Are you going to tell us what you caught in your fishing exercise?
Oh, unfortunately, nothing that day, but it is quite relaxing to sit out on a frozen lake and absorb the first rays of spring sun. I mean, the days aren't long at all.
Right. Okay, so it's time to end. Thank you, everybody who joined this afternoon. And I'll just remind you that we have another webinar at this time in a month. And it's another doctoral award winner who is overseas in the UK and will be joining us by Zoom. And we have this later starting time to accommodate the time difference. Nevertheless, thank you all for joining us this afternoon. Please, if you have any comments or you have any feedback, either directly to Adam about his lecture or to the Royal Society, make use of those links that are on the closing slide. So with that, I'll end this seminar and look forward to seeing you all on the 5th of September for our next webinar.